Good morning, students. Today we are moving on to our fifth unit of Communication Theory 19 EC 403. So let us quickly go through the course outcome of our fifth unit. It is to verify sampling theorem and quantization technique. So with the knowledge of which we will be able to implement various pulse modulation techniques. So as I say, pulse modulation techniques under unit 5, we will discuss about both analog pulse modulation as well as the digital modulation technique. So under analog pulse modulation techniques, we will be looking after pulse amplitude modulation, pulse width modulation, pulse position modulation, and under digital modulation technique, we will be focusing more upon pulse code modulation. So in this lecture, we will focus about the basics of sampling, the definition of sampling theorem, what is quantization, the different techniques under quantization, few compounding techniques, as well as we'll look about the digital modulation system pulse code modulation. So we'll see how to generate a pulse code modulation and how do we recover it. Let us move on to the next slide. Yes. So what is sampling basically? Why do you go for sampling and quantization? Any idea? So as we discuss about sampling and quantization or the need for sampling and quantization, we'll quickly correlate between the conversion of analog to digital. Am I right? So whenever we try to convert an analog, a continuous waveform, to a discrete time, which is a digital type signal, we try to follow processes of sampling as well as quantization. What is the definition for sampling? So sampling is nothing but it is the process of measuring the instantaneous values of a continuous time signal in a discrete method. Okay. So actually we try to sample a piece of data, like we take every sampled pulse here, which is taken from the whole available data, which is continuous in time domain, right? So you can observe the waveforms here, which is shown. So this is a continuous time signal and we try to take a sampled version of this signal, and the second waveform gives you the sampled signal format, and all these are representing sampled values of the above continuous time signal. So I say the continuous time signal is given by x of t and the sampled signal is given by x s of t. Okay, and this x of t is actually multiplied by a periodic impulse trained. So only then we'll be able to get the sampled signal xs of t. So keep in mind, whenever you have an analog input, we try to multiply it with the help of a periodic impulse train. Okay, and then we try to get the sampled pulses. So now, how do we fix the sampling rate? So to discretize these signals, the gap between each and every sample must be fixed. So I try to define this parameter as sampling period or also sampling frequency. So as I say it is sampling frequency, I give the notation as f suffix x, which is equal to 1 by ts, and this ts is the sampling time and fs is the sampling frequency or the sampling rate. So actually this sampling rate is the reciprocal of sampling period, and this denotes the number of samples which are taken per second. So keep in mind that the sampling rate denotes the number of samples taken per second. Yes. So as I said in the earlier slide, we try to reconstruct a digital signal now. Okay. So think in the reverse way. In case when I want to recover back my original data, I need to define how should be my rate of sampling. So for this, we go for one more criteria called the Nyquist rate. So if suppose I consider a signal which is band limited with no frequency components higher than W Hertz, then for this kind of signal, in order to have effective reproduction of the original data or original signal, the sampling rate is fixed as twice that of the highest frequency component, which is your omega hertz. Okay, so I say my Fs is equal to 2 omega. In such a way, I try to define my Nyquist rate. Only then at the receiver end, we'll be able to recover back or reconstruct the original signal. So this sampling theorem is actually stated based on the theory of this Nyquist condition or the Nyquist rate. So the sampling theorem states that a signal can be exactly reproduced only if it is sampled at the rate Fs, which is greater than twice that of the maximum frequency W. So I repeat, please listen. The sampling theorem states that the signal can be exactly reproduced or recovered back only if it is sampled at the rate of Fs. Fs is the sampling frequency which we have defined earlier, which is greater than or equal to twice that of the maximum frequency W hertz. Okay, so here we just, for instance, we try to define a band limited signal and we represent it as x of f. And now we'll try to represent a continuous time signal. So look at this waveform. This is a continuous time signal which is band limited to minus omega and plus omega. Okay, so I consider that in case if my signal x of t, this signal is sampled above the Nyquist rate, can my original data be recovered back? Yes. So based upon my Nyquist theory or my sampling theory, I can very well recover back my original signal if I sample my signal above the Nyquist rate. Okay. So I try to fix the sampling rate greater than 2 omega. Okay, so I say that my signals are sampled at a higher rate than 2 omega in the frequency domain. So this represents the Fourier transform of a signal, or this is a sampled signal excess of t. So I'm able to recover back my original signal without any loss when I'm sampling it at a rate higher than 2 omega. So I'm able to recover back all my original data. Okay, this is defined in frequency domain. Now let us go for the next condition where I try to define my sampling rate is equal to 2 omega. Now what happens? So still I'm able to recover back my original data here. Okay, Fs is a sampling frequency. So keep in mind W is the highest frequency. So here I fix Fs is equal to omega. My sampling frequency is equal to the highest frequency component, and still I'm able to obey my Nyquist rate. So I could recover back the original information without any loss. So I say that this is a good sampling rate. Okay, so this is the signal which is represented in frequency domain. Now imagine the other way. Let us consider that your sampling frequency is lesser than 2 omega, twice that of your highest frequency. Now what happens? Just observe this waveform. So when you observe this waveform, I could find overlapping of information is done here, right? So this leads to mixing up of data or loss of information. This unwanted phenomenon of overlapping is known as aliasing, or you say that you have interference of information due to which we tend to lose useful data, and this phenomenon is known as aliasing, and this is one of the main drawback, and the condition for this is Fs less than twice it of your highest frequency. Yes, so now what is the definition for aliasing? So aliasing can be referred to as a phenomenon of high frequency component in the spectrum of a signal taking on the identity of a low frequency component in the spectrum of its sampled version. So this aliasing is a major drawback we encounter. So now let's move on to learn about quantization. So what is the necessity for quantization? So as we know already, in order to digitize a signal, we undergo the process of sampling, and the next step is to confine our signals, which is like a rounding off process. So where I try to quantize or define some sampling levels. So that is known as quantization, where I try to represent the sampled values of the amplitude by a finite set of levels. So here I convert a continuous amplitude sample into a discrete time signal. So observe this waveform. Okay, so I try to convert this to a digital waveform. So first step is for going for sampling, and the next step is to represent them by a finite set of levels. So you can just observe this waveform. Here is where you can just find some steps like waveform, right? Like, or like a staircase like structure. So this is nothing but the quantized waveform or the quantized signal. So the quality of our quantizer output mainly depends upon the number of quantization levels we take. And this width represents the quantization size or the step size. Okay, the discrete amplitudes of the quantized output are known as the representation levels or the reconstruction levels. And the spacing between two adjacent representation levels is known as the quantization size or step size. So as we move further, we have further two types of quantization. One is uniform and the other one is non-uniform. Yes, can you observe this? So this is an quantized signal waveform or it's a staircase waveform. So I'm able to see a quantized signal here. So now let me just discuss what is uniform and non-uniform quantization. So when it is uniform quantization, here we define the quantization levels uniformly spaced. Whereas in case of non-uniform quantization, here the quantization levels are unequal and mostly the relation between them will be a logarithmic function. Okay, and under uniform quantization, we still go for two types which are known as mid-rise and mid-tread type. And the first waveform represents mid-rise and the second one represents mid-tread type. What is mid-rise? So look at this waveform, the first one. So mid-rise type is so called because when you observe the waveform, you just try to point out the location, so or the origin here. So this is the origin. The origin exactly lies in the middle of the rising part of this staircase waveform, right? Can you observe? It lies exactly in the middle of this rising part. Am I right? Also, the quantization levels we define will be of even numbers here, whereas the quantization levels we define in case of mid-tread type will be of odd number. And also, look at the origin. The origin lies in the middle of tread of the staircase waveform. So this is the main difference between mid-rise and mid-tread quantization, and both are coming under uniform quantization. Yes. So next comes quantization error. So definitely whenever you define a system, we'll encounter with some erroneous factor. Am I right? So as you take the difference between the input value and its quantized value, we come across an error which is defined as quantization error. Yes. So this is the original quantized signal and the waveform, and this is how we represent our quantization error. So normally, whenever you measure this quantization error, for say for an instance, a music signal, you have the signals to be keep on changing continuously, right? And whenever we observe some quantization error, we try to observe some irregularity, and this kind of noise or error is known as a wideband noise or quantization noise. Yes. So far we have discussed about the concepts of sampling, what is sampling theorem, Nyquist rate, what is quantization, and the different types of quantization. And the next topic of discussion will be about digital pulse modulation, where we will focus on pulse code modulation.